All right, good morning.
So this is ELE 482 CMOS VLSI. Welcome back from break. I hope you enjoyed it. So far. For those of you who don't know me, my name is Dr. Morrison. I responded to Matt just fine. I don't insist that you call me Dr. Morrison. Most of you have either had me for computer architecture or for advanced signal systems. So the general idea of what we learned in that course, we started at MSI level, which is medium scale integration, 10 to 100 transistors, putting together gates, then building up to arithmetic logic units, controllers, and then building up to this concept called VLSI, which stands for very large scale integration. So now you know what the second half of that CMOS VLSI stands for. In this course, we're going to start at the transistor level and build up. So we're actually, in the first few lectures, we're actually going to learn how a transistor works, a MOSFET, stands for metal oxide semiconductor field effect transistor. So CMOS, the general idea is that you have to work them in complement. You have a pull-up network, you have positive metal oxide semiconductors, and you have negative metal oxide semiconductors, and they work in complement, CMOS, complementary metal oxide semiconductor. So you can work these pull-up and pull-down networks. And we're going to be building these up. In this course, we're going to start to talk about length and width ratios of transistors and how that impacts the ability of the circuit to be able to go from 0 to 1 in a certain amount of time. How much does that, what's the current that needs to be applied in order to make that occur? Then you're going to start putting those together. We're going to be building cells, like gates, certain logics that you can actually use to put together to build a much larger circuit. From there, we're going to be learning layout. Additionally, we're going to be going over Verilog. For those of you that that course last semester, we did VHDL, which is an acronym within an acronym, very high-speed hardware description language. In this course, we're going to learn something called Verilog, which is a little different. It's another hardware description language. It's a language we actually lay it out. If you're using a hardware description language to lay out an embedded system, like on a board or a Raspberry Pi or anything like that. Well, Raspberry Pi you probably use C, but if you're laying out an embedded system board, you probably use VHDL, which is very good with coordinating pins. If you're taking a hardware description language and synthesizing it down to an actual chip, like we're going to learn about in this class, Verilog is a much better way. So what we're going to do is we're going to take a simple version of Verilog. All of you take my course to recognize the term MIPS. Okay, so if you've actually kind of gone through the textbook, you see that this course actually teaches a kind of an overview of a form of MIPS called a multi-cycle. And you can actually make a simple simple Verilog code, which I'll show you how to do. And then you can take that and synthesize it. There's a free word called electric. Then you put that, and it'll actually show you the chip, it'll show you how much power you consume, shows you the area, shows you the exact layout, I'll show you examples of electric. So I don't want this course to be as work intensive as the Advanced Signal Systems course was, because that's a required course. For this course, I want you guys to get familiar with certain tools. We're going to learn about HSpice, we're going to learn some Verilog, you're going to get familiar with electric, so that way you can build your resumes. That way you start interviewing for jobs, you could have a really strong background for the number of tools. If you say you can do these number of tools, become more desirable to employers. Now, for those of you who've taken my course before, you recognize the terms topic objectives, example questions. For those of you who haven't, these are daily assignments. So you're every day. I insist they're handwritten because they stick in the head better. During the lecture,
I'll actually indicate. Let me scroll down a little bit. So, first TGOs 1.1. I want to define and differentiate between small scale integration, medium scale integration, large scale integration, and very large scale integration, right? You'll handwrite this out, and you notice in Blackboard. So this is the undergraduate section. Under content, I have the syllabus, topical guide objectives, example questions. I'm going to call this extra credit for graduate students. This is a required thing. But the topical guide objectives, we go to section 1. I'm finishing up the course, but section 1.1 is going to correlate directly to what's in the lecture. This is done so that way you can study and build up the fundamentals that you will need to do more complex problems that you will need to do on an exam. Additionally, by looking at this, you'll
will know precisely how I answer questions. So there's no, I aim for no ambiguity. I want people to know precisely what I'm asking so that way they can give me the precise answer. My job is to put the knowledge into your head and then prove it's there. So when I ask you ambiguous questions or questions that don't make sense, and I haven't necessarily proven that the knowledge is not in your head. So this is my way of helping you be straightforward. I've already mentioned a lot of reasons why it's just they're handwritten, because it sticks in your brain better. The other one is to prevent what I call academic bullying. And I'm not really worried about anybody in this class. I've heard good things about all of you, but the general, what happened the first semester, I used this teaching method. I allowed the students to type it, and what happened was one of the students was saying, give your typed up work and handing your business as well. And so what I want to make sure is that nobody feels as though they are being compelled to do somebody else's work for them. The easiest way for me to ensure that is to insist that homework is handwritten.
The next part is example questions. So these are things that we actually cover in class as well. So in the first section is going to be draw a 2-input NAND gate using a CMOS pull-down
network using a transistor layout. I've already kind of alluded to this, what the CMOS actually means. And so in example 1.1, when we actually get there, I'll get to your question in a second. When you get to see it, the whole step is you actually kind of work through it and the problems build up. And they build up to these combined concept questions that are very good questions for examination. So TGOs are the fundamentals you need to do the example questions. The example questions are going to be put together towards strong exam type questions. Yes?
We're going to do groups.
I'm not sure yet. I'm finishing up the project descriptions this weekend. Okay. So, how many are now in the class? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. No, okay, so that's 11. So that's, I'm still waiting to find out. There's a course that there might be a couple more students registering, so that way I can figure out precisely the ratios of what groups I want to create. There'll also be other things. Actually, there will be some level of groups that just need to know the number. There's going to be 2 things we're going to be working on these kind of coding projects, and there's also going to be something we'll be working. Each group is going to be doing blogging on a website called SemiWiki, and it's run by a gentleman named Dr. Daniel Denny, who is the innovator of what's known as fabless design. So you don't have a fabrication lab. There's only a few fabrication labs, but you want to design a computer chip, you're going to use a lot of these tools that we're doing. And the innovator of this is Daniel Denny. He's wrote a very famous book called Fabless, and he runs a site for professionals who work on this kind of work called SemiWiki. And when I met him this summer, I was talking to him about possibly having students work on it, and he's been dying to try to get universities to do this for a while. So what's going to happen is your groups are going to pick a project, and you're starting by writing a 500 words to 1,000-word blog post. And Dr. Denny's going to encourage professionals on there to be commenting on it and interact with you over the course of the semester. So get you in contact with professionals, people who might be able to give you jobs, give you advice, give you knowledge, things that you didn't understand, things you didn't know. And in the last couple of weeks, the groups are going to present what they learned during the SemiWiki posts. So that way, you're learning things that are just outside of the scope of what you're going to find in the textbook. So I'll get to that. I just got the code this morning. When you register, you'll register on the website. You'll say that I referred you, and then he will approve you. So now you have an in that no other CMOS student in the country has.
So this thing I have here that called extra credit. Basically what's going to happen is in the course of the lecture, it's going to say grad 1.1, grad 1.2, kind of that kind of thing, because for graduate students it's going to be required. What this is they're asking 1 to 2 paragraphs of either a video. For example, 1.2 is a video showing out the fabrication process for Intel's 22 nanometer transistor. 1.1 is a write-up on the differences between CMOS transistor, what's known as a FinFET transistor. For graduate students, I insist it's going to be turned in along with the topical guide objective. For undergraduates,
this is extra credit opportunity. So you can do this, and every time I'll add a number of top of loop guide objective points, and this will help you learn some things that are not necessarily in CMOS. So hopefully, if you take advantage of that opportunity, you could be even more well-rounded. So I'm going to try to pick some things that are recent, that people in the industry are talking about that you might want to know about. So.
Okay, does anybody have any questions before I kind of jump into the lecture?
Oh yeah, don't cheat. I hope that would be a problem. Anything else? Okay, good. What's that? Oh yeah, pizza party. Last day of semester. So the undergrads will be presenting on Sunday. The grad students will know that that's actually in the syllabus. And the grad students will present on a paper from IEEE, kind of a recent research project. There will also be, at the end of the semester, by that point, you'll have all the exams done, you'll have done your presentation, and I will have your final grades ready to go. I will have pizza ready for you. You'll eat pizza, and then I'll call people up to the front. I'll look you square in the eye and tell you what your final grade is. And that's a personal integrity thing for me. I know professors not here at University of Mississippi, but elsewhere, who have given students grades that they didn't deserve for a variety of reasons. Grudges, they didn't like so-and-so. It's important that I have the personal integrity to look square in the eye and tell you this is a decision I've made that will impact your future, right? So.
And also you get pizza, so that's a plus. So, yes?
All of the other content on Blackboard, the topic objectives, example questions, extra credit, those are all listed under each folder. And as we go through the course of the semester, I'll update them by section. And so what's going to happen is you can actually refer back to them. I am recording the lectures, so I will post them on Blackboard. I will post the assignments. So the topical guide objective will be 1.1 through 1.6 or whatever we cover today during the lecture, or the end of the example questions. I'll post that, and I'll post a link to the YouTube page. So you can actually go back, read through that, then you have the links available so that way you can study for exams. I do not, the one thing I'm adamant about is I don't post the PDF notes because then those get passed around and that discourages class attendance. If you come to class regularly, I'll help you. If you skip my class a lot, not so much. Fair?
So yeah, that's how
it works. So I send out an email notification every time, so you'll have the homework. Any other questions before we begin?
Okay, so this is CMOS.
This is a picture of an example of the very first point contract transistors developed at Bell Labs. The two people who developed it, named John Vardan and Walter Pertain, they won the Nobel Prize for designing it. In the action, it almost became a classified military secret,
but they decided to publicly introduce it. And the actual wording from the paper, they said, we haven't called it the transistor, and they actually took it out to spell out transistor, even though the wording for transistor is right next to it, because people apparently can't spell the words they just read. Because it is a resistor or semiconductor device which amplifies electrical signals as they are transferred through it from the input to the output. So they won the Nobel Prize for this, and so this gentleman here is a guy named Jack Kilby.
And he is the first person to invent an integrated circuit, and he did it at Texas Instruments. And what happened at the time is before the integrated circuit with the silicon chip was done, there's this problem called the tyranny of numbers. And it meant that computer engineers and the electrical engineers thought that every single component in a computer chip had to be connected to every other component in a computer chip. That's why these computers that you see from like the 50s and 60s were these huge, like fill up entire rooms, because they felt they had to connect all of them. So
what he did is he actually just manufactured the circuit en masse on one piece of silicon semiconductor, and that allowed them to actually just have the circuit flow logically the way you have
learned in your courses now.
And Jack Kilby received the Nobel Prize in 2000 for this. And this is the actual picture of the first integrated circuit.
That was designed by Texas Instruments, designed by Jack Kilby and Texas Instruments. For those of you who've taken advanced digital systems, or probably even you know JK flip-flops. JK flip-flops were also invented by Jack Kilby. He was just messing around trying to improve on S latches and D flip-flops and came up with the JK flip-flop because it covers all the possible input and output combinations and eliminates the toggling problem, especially with D flip-flops. So,
same guy who invented the integrated circuit was the same guy who invented the JK flip-flop. Okay, so TGO 1.1,
small scale, medium scale, large scale, and very large scale. Small scale, logic circuits that use less than or equal to 10 transistors. So it's kind of just a number to think of. You can think of this as a chart. Medium scale takes from 10 transistors to 100 transistors. So at the small scale, I'll show examples of small scale, medium scale, large scale, and very large scale integration. You can think of it as hardware, NAND gates, AND gates, all of these logic circuits that require less than 10 transistors. Once it becomes greater than 10 transistors, use MSI circuits. So you're putting gates together to build logic. So full adders, full subtract, comparators, things of that nature, decision circuit. Once you get to large scale integration, that's where you start creating control units, arithmetic logic units, memory set elements, registers. And as you put all these together to form a data path for a computer, this is when you get to very large scale integration. So that's when you're getting to greater than or equal to 1,000 transistors. So VLSI is 100 to 1,000, MSI is 10 to 100, and LSI, small scale integration, SSI is less than 10, or less than or equal to 10.
All right, so this is an example of an inverter here at the bottom of the page. So
this is an example of a pull-up and pull-down network. This here is what's known as a pMOS transistor, and this is what's known as an nMOS transistor. And the idea is you think of them as actually like switches, like light switches, where the idea is you want a 0 on the input and a 1 on the output, so the inverter. Now we have VDD, which is the supply voltage, which is the logic 1. So we want this to flow through here when the input is 0. And when the input is 1, we want this VSS, which is ground, which is logic 0, to flow through the nMOS transistor. So we're going to define a pMOS transistor as a strong passer of zeros, meaning that this is what's known as the gate. When a 0 is put on the gate of the pMOS transistor, it will pass whatever values on from the source to the drain. So if you here, we have it hooked up to 1. So if we put a 0 on the input, it's strong. It'll pass the value to the 1. And nMOS is weak when a 1's on the input, meaning that we're going to learn about channels. It does not allow it to go through, so they won't mess with each other, which means that 1 will go on the output here. When you have a 1 on the input, pMOSs are weak. nMOS is strong, so this cuts off. The 0 comes through here, and then you have 0 on the output. So that's how the transistor actually works. So this is an example of a small-scale integration circuit. I wasn't going to go into detail in this course about the actual physics behind how that works. So MSI, so this is 10 to 100. So we have some small examples of adders. We have a decoder, some carry-out circuits, and output. So it's kind of a small version of a arithmetic logic unit. So you have AND gates and NOR gates and inverters here. So all of these SSI circuits are being put into these gates, which build upon each other, and then we can create an LSI circuit. So now that we have...
Look familiar?
Yep.
Hey, for those of you who haven't had my class before, this is the MIPS data path. We have the instruction memory here. We have an adder. Registers store local memory. Arithmetic logic unit and adder to perform branching instructions. Then we have data memory, so it's like the higher DRAM type memory, or the memory hierarchy. and then we go back and do it again. So without going into too much detail, this is an example of an VLSI circuit. So a VLSI circuit is a layout of the Intel 4004 processor. And what you're going to do for one of your assignments is you're going to take this small version of this Verilog code, and you're actually going to produce this layout of the next data path. So, are you all familiar with Moore's law? Okay, this is Moore's law. So basically, as the year goes on, the number of transistors that can fit into a certain amount of area increases, doubles every 18 months. And it's obviously not a physical law, it's just motivation, but you did kind of notice it was on the semi-logarithmic scale, so this is 4004. You kind of noticed around here, 808, we're doubling this every 18 months. And now we're starting to get Core 2 quad-core processors, 2007 today. So now we're getting into all these quad-core processors in order to be able to take advantage of parallelism on a single chip. All right, so this should say end 1.2. So here's the actual chemistry of what's going on inside of transistors. Silicon, it forms covalent bonds. It's a group 5 element. So that means it can form one bond on each side, right? So if this is the silicon in the middle, it has 4 valence electrons and it can form 4 bonds. So if you have silicon, you can actually create this lattice structure where they're all kind of in a row like this. So this one has 4, this one has 4, this one has 4, this one has 4. So it's very strong in that current doesn't really flow through it very well. So how do we change this? It's this process called doping. We're going to put arsenic and boron atoms into the silicon lattice in order to create what's known as electrons and holes. And what's going to happen as voltage is placed on the different voltage difference is placed on the gate, we're going to create a flow of these holes. They're actually going to move through this lattice in order to actually create the current flow. So current electrons go one way. Holes, which are, if you have a plus and a minus here, your extra electron is going to be there, and a hole is going to be a place where electrons can go. So you want to be creating, if you heavily dope a silicon transistor, if you heavily dope silicon lattice, you can create a transistor by using this metal oxide semiconductor. So to read 1.2, it states silicon is used as the basic starting material for the most integrated circuits. Pure silicon consists of a 3-dimensional lattice of atoms. Silicon is a group 4 element, so it forms covalent bonds with 4 adjacent atoms. So we will define dopant as impurities placed in the silicon, this is 1.3, crystal to improve the conductivity. And the dopants moving through are going to create what are known as carriers. These are the free charges moving throughout the silicon. Electrons are negative charge carriers, and holes are positive charge carriers. Before I move on, does anybody have any questions about this? I know I'm kind of getting into a little bit of chemistry. Some of you may have thought you're done with this after freshman year. I'm not going to expect you to remember everything. I'll tell you everything you need to remember the chemistry part of it. So there are these things that exist called covalent bonds, and silicon makes them. So at the bottom, I'm going to scroll past 1.2. So we first have an example here of N-type semiconductors. These are silicon-based semiconductors with group 5 elements, such as arsenic in the middle. So what happens is instead of having silicon here, you're going to have arsenic, and you're going to have this extra hole. The 5th valence electron is loosely bound. So
it's going to form all of these bounds like it normally does, and it's going to have this extra electron loosely bound inside of the lattice structure. And I don't know if you can see this, but when you're watching the video there, you can see that arsenic has an extra plus and silicon has an extra minus there. So thermal vibrations created by voltage the lattice will set the electron free, leaving a positively charged arsenic ion and a free electron. So now you've got a charge carrier. You have an electron floating around the circuit. And as you create voltage, it wants to go towards the positive, right? That's how you create current.
And so let me read 1.6 for you too. P-type. So now
we're starting to create our complements. So our N-type semiconductors, I showed you the inverter, the N-type semiconductor, which is tied to ground. So what's going to happen is you want 0 pushing these electrons away, with the negative flying away, right? So ground to the output. 1, you want the positive, so you're going to want these holes flying through. So that's where these P-type semiconductors come in.
P-type semiconductors are silicon-based semiconductors with group 3 elements such as boron, which can borrow an electron from a neighboring atom. That silicon atom can borrow another electron from another atom. The whole acts as the positive carrier.
So the fact that it can borrow another electron, so let's say Kevin is an arsenic and I'm boron, right? And I'm like, hey, I really want your soda. And since he's my grad student, he's going to give it to me, right? So this is what works. Okay. Well, since Kevin has the soda and I don't, this represents an electron, and I represent a hole, right? So it's going to naturally flow to me when there's some sort of voltage, right? So that's how this kind of works. And so the way CMOS circuits are going to work is you're going to create these transistors in such a way that you want to create these networks to work specifically when you have certain logic values. So later on in the section, we're actually going to be creating 2-input NAND gates, 3-input NAND gates. We're going to actually take a function and a small function and actually create a circuit with it.
And so as you can see in this diagram, we have a boron dopant here and is able to create another electron. I mean, a hole there. So I'm going to scroll past 1.5. So
a diode, let's see, we have markers here. So I know that the diagram is down a little further, but the general idea of a diode is you take positively charged doped semiconductor and a negatively charged semiconductor, you put them together to try to create that current flow, and then hook them to a voltage. So if you hook it up to a positive voltage, so you want to hook the positive voltage to the P-type, hook the negative to the N-type, and then the current's going to flow when you officially hook it up. And if you hook it up the other way, remember I was talking about pMOS and nMOS semiconductors are strong, pMOS is strong conductor of 0, nMOS is strong conductor of 1. So if you hook it up the original way, you're going to have strong current flow through the diode. If you hook it up the other way, it'll actually stop the current. So the positive
is known as the anode, and the negative type, N-type, is known as the cathode.
Well, for those of you who haven't had me for a lecture before, I don't mind questions. Don't be shy. I'd rather you ask the question and there's a question that makes you sound like an idiot. It's better sound like an idiot now than during the exam. So, and I take time to answer questions. I don't mind. I want everybody to understand.
Phosphorus is somewhere.
I mean, it can be. The two most common are arsenic and boron, just because of their proximity to silicon in the periodic table. They're the ones who react the most. You got the highest creation of holes and electrons, and you also have to worry about atomic weight because you want to make sure that it's light, and especially when you're using computer chips and phones. Heat, power consumption, heat, area, and weight comes into play. So if you're using a very heavy element to do this, it kind of takes away from it. That's also because if you put a huge atom in the middle here to dope it, suddenly it's going to take up a lot more area because of the larger nucleus. So it's going to throw everything off. So it's going to be more balanced using arsenic and boron. But I'll look into that for you. It rings a bell, but I don't know off the top of my head. Okay, any other questions? All right, so I'm going to scroll past 1.6. And so just as I explained before with the diode, you hook up a positive voltage to the P-type semiconductor. When it works, the electrons flow this way, the holes flow this way, and you have current flow. And this is the logical equivalent of a triangle with a hole there, a line there, and it flows just fine. I scroll down a little bit. We see that if you hook it up the opposite way, it actually stops current flow because you're not going to create that movement of holes and electrons in the circuit. So the charge carrier is usually going to stay in place. And so the two terms for that, this is not TGO at all, forward bias and reverse bias. As a potential thing for a semi-weekly topic, forward biasing and reverse biasing in CMOS is actually used as a method to try to either reduce power consumption in the case of reverse biasing, or forward biasing, improving what's known as rise time. So you can actually talk to them about how does forward biasing or reverse biasing impact circuit operation. You can take a paper or article or something you see, say, hey, this is really neat, and write a blog post about it, they'll ask you some questions, you go, okay, I mean, try to respond as best as you can. You know, part of this is it should be fun. You should be trying to figure out new interesting things. So I'll try to guide you for certain topics as things like that come up. So for a long time, these diodes and what are also known as NPN transistors. So we won't go into NPN transistors, but you're basically just putting another N-type on the other side. So you're trying to create this base and gate and drain that we had before. And those work kind of well. CMOS, when we're going off of these metal oxide semiconductors, tend to work a lot better. But NPN transistors, or what is known as junction field effect transistors, JFET, they work at much higher temperatures. So there's research actually being done at NASA to try to use NPN transistors on computer chips on Venus. So they're trying to actually make these work, and they're trying to actually send them. Because if we send CMOS computers like they did in the past, in the 70s, they burn up after like 10 minutes. So it's not going to help you collect much data. So there's sometimes we put a probe on there, we get one photo of the surface, and then there goes your $100 million project. So how do you use different properties of these metal oxide semiconductors in different environments? Things are going to work differently on Venus, where it would go up to 140 degrees Celsius, as opposed to Mars, where it can go down to like 120 degrees Celsius. So there's this huge range of temperatures in space, and people like you could potentially help them make that happen. So, but in the meantime, the computers that we use on Earth are known as CMOS, and these use what are known as metal oxide semiconductors, field effect transistors. So whenever I say MOSFET, that's what this is standing for. You can't see that now?
No, I'm good.
Oh, and for those of you who haven't had my class before, I'm bad with names at first. Just tell me a number of times, and eventually I'll get it. Probably after grading your assignments a couple of times. These were invented in 1963, and there are 4 elements to a MOSFET field effect transistor. You're going to have a gate, which I kind of alluded to earlier. Is there something I can do to help? Pointing. Oh, look at yours. Probably my hair is no, you're good. Fair enough. Don't stand up. So there's a gate, which we kind of alluded to with that pMOS and nMOS inverter. So you put the voltage on the gate. You have the source, which is where you want it to flow from, and the drain, which is where you want it to flow to. So the pMOS transistor, the source was tied to supply voltage, VDD. In the nMOS transistor, the source was tied to ground. And then the drains are tied together, which is why we can control the specific output.
So the actual definitions I have for TGO 1.8, the gate is a polysilicon conduction layer used for determining transistors and an insulation layer of silicon dioxide. The source is the input pin, the drain is the output pin, and the body is the actual silicon wafer. So
after you guys write this down and ask if we can go over a little more, I'll actually show you a diagram. So on your exam, I will ask you to be able to show me the what's known as the transmission gate level layer of a inverter. That's when I say transmission level, you'll see that in the subsequent TGOs, the wording. What I mean is I want you to actually draw the gate. I want you to draw the silicon oxide in between the gate and the body. I want you to draw me the source and drain. And we're going to actually tie those together. We're going to see the gate level, the transmission level, and then we're going to be going into something called stick diagrams towards the end of this section, which you actually see kind of how it's actually physically laid out. And to be a little more clear on stick diagrams, if you're trying to lay out, this is one of the things that I feel is important to teach in this class because I want you to teach you good design principles. Stick diagrams are very, very useful in if you design a good stick diagram before you actually put anything into the computer, before you actually lay out the circuit. If you have a stick diagram, you may have to force you to design rules to make it work, but there's an algorithm to do that too. But you'll actually have the actual physical layout so you know the steps that you need to follow. So it'll save you a ton of time in actual design.
Okay, so this is what a transistor actually looks like. So nMOS is a type of MOSFET where the channel exists between the source and the drain when the high voltage is placed on the gate. So what's going to happen here, and I'm actually going to describe this in a diagram a little later, but here's what's actually physically going on
inside the transistor. So the body in an N-type transistor is a P-type, right? So what's actually happening is when you put a positive value on the gate, you're going to push all your holes down. And what that's going to allow is you have the source and the drain here are actually doped heavily with electrons. What's going to happen is it's actually going to create a channel here. And what's going to happen is your potential is going to flow from your source to your drain. Same thing in pMOS transistor. If you put a 0 here, you have all of these electrons, right? The same thing, you're going to push them down, and then you have positively charged source and drain, and it's going to create a channel between the source and the drain, and then you can have it flow through. And we're going to be learning about something called terminal voltage, which is what is the minimum voltage required to be placed on the gate in order to create this channel. And you're going to, when you play with H-Spice, you can actually determine that exact voltage by seeing simulation. So if you have, once you hit that terminal voltage, you'll actually get a spike on the output based on what you want. Before, it would just be transient. So you can actually perform experiments using something called Monte-Carlo simulation to actually find out that exact value. Does anybody have any questions on
that make you part of the computer?
No. I'm sorry, yes. Yes. Sorry, this is, actually, I'm not sorry. Sorry, not sorry, actually. Wrong place. No, this is actually really important. This is really important to understand these kind of the transitions at this level, because this is physically demonstrating how it works. If you're going into any kind of computer engineering job, you should be able to produce this from memory, especially in Java. Yes.
So is that glass? Is that SiO2? Is that what that is?
Mm-hmm.
So it's actually an insulating layer.
Yes.
So whenever you put a voltage on the gate, it just the field pushes creates a channel.
Mm-hmm. If you're hearing this thing, this is a very good question. A little later on in the lecture, we're actually going to be going into the actual step-by-step process of fabricating it, and that's exactly right. You want to create this insulation layer, because you want to make sure that you're not kind of, because you're tracking these up here. Let's say, okay, so let's say you have an N-type, right? So we put a 1 on here, push these down, and we have a channel. What we don't want is we don't want these kind of go back through the gate. So we use that SiO2 there as an insulation. That's a very good question. Does that make sense?
Okay, so let me read the word for word nMOS and pMOS definitions for you. nMOS is a type of MOSFET where a channel exists between the source and the drain when the high voltage is placed on the gate. And pMOS is a type of MOSFET where a channel exists between the source and the drain when a low voltage is placed on the gate.
So what we're going to learn next is how to put these two transistors together to create an inverter. Because you're going to want the output drains to be tied together. So you're going to have your input, so your A input and then your Y output. Your inputs are going to have the same value for the gate, right? And then, I'm describing this a little down here already, some of you, right? But when you put in a 0, what's going to happen is it's going to go to P-type and N-type. The N-type is going to keep pulling these up so there will be no channel. Here, it'll push them down, it'll create a channel, it'll come from the supply voltage, and you have a 1 on the output. So that's how you create the inversion. Same thing, you put a 1, you go to the P-type, the 1 isn't going to push the electrons down, it's actually going to attract them, so you're not going to have a channel. Put a 1 here, pushes the holes down, the channel is created, and then from supply voltage, from the ground, it's going to flow to the output. So that's how you create the inversion on the physical level.
Okay. And so CMOS, as I said here, stands for complementary metal oxide semiconductor.
It's amazing to me the number of people where you go through a whole CMOS class and you ask them, what does CMOS stand for? They have no idea, even though they've been doing CMOS the whole time.
And so the first graduate assignment and extra credit for undergrads is what are the differences between a CMOS transistor
And a FinFET transistor. And a small illusion, this link is available on Blackboard for undergrads under extra credit, for grad students under grad assignments. But this is a really good description by a company called Synopsys, and you'll be working with some of their tools in this course, particularly HSpice, giving insight into these 3D transistors where you're trying to use multiple gates in one decision logic element. And to kind of go back to your question that you asked, I'm sorry, what's your name? Jason. Jason. Okay, let me go back to the question that Jason asked. So once we have so you'll be working a lot with like 0.25 micron feature size. We'll talk about feature size in a little bit. One of the challenges that we've dealt with when we got down to 22 nanometer is something called punch through, where the glass layer wasn't able to hold the electrons anymore. And so that's when forward and reverse biasing actually became very helpful. How to apply biases to the substrates in order to actually prevent punch through. So another potential topic
for your blog thing. Okay, so I've told you pretty much everything in TGO 1.10 already.
I've included this because this is a very common interview question. Describe and draw for me how pMOS and nMOS transistors work, particularly as switches. So, as I mentioned before, nMOS passes a strong 0, pMOS passes a strong 1, right? And that applies to the gate. So when I say that nMOS passes a strong 0, when you put that value on the gate, whatever's at the source can go to the drain through the channel. But it's degraded or weak 1, meaning I put a 1 on the gate, it's going to push down the positive holes in the bolt, and will not be able to create, we'll raise them up so it won't be able to create a channel. That's what we mean by degraded or weak 1. Which means that nMOS is ideal for the pull down network. Recall the pMOS and nMOS transistor for the inverter, sorry, pMOS and nMOS inverter. The nMOS on the bottom is pulled down towards ground. nMOS is ideal for pull up towards the supply voltage. That's because it passes strong 1. No, I don't. If it's greater or weak 0, pMOS ideal for the pull up network. So the idea is you put it on 0, it's going to flow through.
Here's an example. So for nMOS, you apply a voltage to the gate, you apply a 1, it's going to turn on, so it'll flow through. When it's a 0, it's going to be off. pMOS, you apply a 0 to the gate for pMOS, it'll be on. When you apply a 1 to the gate, it'll be off. So
it's going to flow through. Think of it as like a toll bridge. Okay.
Wait a minute. Let me look ahead. I'm going to look ahead real quick, and I'll come right back up. Okay, so I'm
going to explain 1.11 as well. 1.11 as well as how the channels are actually created.
So before I show you that, does anybody have any questions on anything we've covered so far? So for those of you who've had my class before, what is that kind of, when I put little 4 stars there, what does that typically mean? Yep. So these types of questions.
This is very good. This is showing you actually understand precisely how you can, by asking this question, 1.11, describe the transmission level of nMOS and pMOS and how the channels are created. Well, 1.11 will have the exact wording. You can describe to me, understand gate, source, and drain. You understand what a transistor is. You understand what pMOS transistor is. You understand what an nMOS transistor is. You understand the physics behind it. You can tell me you understand holes. You can tell me you can understand electrons. This is a very good comprehensive type question in one drawing. Does that make sense? So when you put a 0 on the N type, it's just like the switch before. Positive come up, nothing happens here, no channel. When you put P type, you put a 0 on there, then electrons are forced down, and you create a channel between the source and the drain. And the more strong the voltage on the gate, the larger the channel. So I was talking about that terminal voltage. You're going to create a large channel over here, but it's going to get smaller and smaller until eventually it finally reaches. That's where that terminal voltage is. It reaches that first point where you actually have the channel created. And then for N-type operation, you put a 1, it creates the channel again. And for P-type, you put a 1, it's going to raise up your electrons, so no channel can be created. Yeah.
So you said before that nMOS passes a strong 0.
It should pass a strong, yeah. Okay, so passes a strong 1, and then weak 0. And p-type is strong 0, weak 1.
Okay. 110's backwards.
Is it? Okay.
That is correct. So this should be a strong 1, weak 0. Yeah, there you go. Strong 0, weak 1. And the diagram is correct. So okay, this pretty much just describes everything we just talked about. And this is a small little diagram of what the pull up and pull down networks are.
You get your set of inputs. The same inputs go to both the pull up and pull down network. The pull up network has CMOS transistors. The pull down network has nMOS transistors, and then based on that, you'll have one unified output.
Okay, and so I've already kind of alluded to this, but now that we now know what's physically going on at 1.12,
This is the transistor, again, 0, so we go to pMOS and nMOS. 0 is strong, so it passes through, right? So now the channel is created in the pMOS transistor, and we're able to create the flow from supply voltage to output. When it's 0, nMOS is weak on 0, so therefore ground will be stopped. For 1, for pMOS, it'll stop because pMOS are weak capacitors of 1. But nMOS is strong 1, so it'll pass the ground through the channel from the gate, from the source to the drain to the output. So you see how everything's kind of starting to come together towards building all the miracle of electrons and holes to make little zeros and ones. Okay, so I'm going to scroll down a little bit to here. Okay, so at the bottom here, this is the actual physical layout of an actual inverter. So the entire substrate is positive, right? And then here we have our nMOS transistor on the left, where we have N plus and N plus, right? So we have our source and our drain. And then the drain is going to come over here to the silicon oxide, right? So we have the polysilicon here, that's our input. There we have polysilicon here. And then we have our output value for Y. Now, for the pMOS transition, this is our pull-up portion. You have your source and your drain, and they drain to the same place, right? And so, for that, you have to create an N well, right? Specifically for the p-type transistor. And this would be tied to supply voltage, and this would be tied to ground. And we're going to be learning about metals. In this, how you can tie metals to pins. These are pins here. You can actually fabricate that in order to create a circuit. So let me scroll up a little bit.
you don't have to draw this little diagram here. But I have just described what's going on here. When zeros are put on there, it's going to flow from, I'm probably almost sounding like this is ad nauseum at this point, but supply voltage will flow from through the pMOS transistor when you place a 0 on it. You place 0 on it. Here at the nMOS transistor, the channel is cut off. And when it's a 1, it'll be the exact opposite.
It's not flowing into the class. So
No, this is, I took this from the slide. I have to see what's going on here. I don't think those are the same though. It's a different pin. Okay, so it's, yeah. So basically, I took this from the slides.
The general idea is that there's going to be something called a pin here, and so this isn't totally complete. The pin is similar to, see how this polysilicon here is surrounded by glass? So there's going to be a pin here. That's a good question. That's a fair question. What's going to happen is you're going to be learning how to create contacts with something called vias. For those of you who had before, right now the I believe button is in full effect. For those of you who haven't, we haven't covered something, and I know it's going to be covered later. Press the I believe button. I was in nuclear power school. It probably sounds a little disturbing that they told the nuclear power people, I believe. But we will get to this whole concept of contact. But you're going to have contact here, you're going to have contact here, you're going to have contact here that allows you to actually properly transmit. But you're going to have this here to ensure, basically to ensure that you're not having the doped source and drain flowing back up through the polysilicon. You want it to flow this way. And we'll actually kind of go through the whole process of fabrication. That'll hopefully clarify things for you. And we might actually be able to do that without, because the fabrication isn't actually any topical guide objective. So it's kind of, you can sit back and watch the process. And then the same thing with one here. Okay, so creating a complementary network for more than just an inverter. In order to do that, you want to make a quick review of De Morgan's laws. Recall that negative P and Q is equal to not P or not Q. Q never, ever, 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 ever effing equals Q naught. Thomas referred to a story when we were talking about flip-flops in nuclear power school, and this senior chief man, he sounded a lot like Martin the Martian, and we were working on states where you're trying to determine when it's Q and when Q not. So he trying to emphasize over and over again that they should never be the same. Q bar is supposed to be the opposite Q. So at one point, somebody did kind of, I'm going to go to Thomas and I'm sorry. But somebody solves the problem and he comes out with fourth one. He just jumps up on the table and goes, Q never equals Q max. So I never make that mistake again because it was kind of horrifying. I'm sure it was for you right now. Great man, but I was like, oh, fine, 1 and 0, whatever this name, just stop. But so the other portion of De Morgan's law is if not P or Q is equivalent to not P and not Q. And by using these De Morgan's laws, you can actually figure out the exact layout of the transistors. So these steps are 1.15, this is the algorithm. This is the thing that I wish I had been taught when I took this course. You start out with your equation, right? And so nMOS inputs are ANDed together. I really wish I had a marker. I can pull up a example here. So accessories, notepad. So let's say we have A, B, or C. Very simple example, right? So we're going to start with a pull-down network. Actually, that's a better example. Let's do not. So we're going to start with not A and B or C, right? And so the reason why you want to start with not is because since we've proven that nMOS transistors are weak with zeros, they're strong with ones, and pMOS are weak with zeros, strong with zeros and weak with one. This means that this would like a conventional AND gate. There's no flow through the circuit where you can just do it with the normal pull-up and pull-down network. You're going to do a NAND gate and then use an inverter. And we'll demonstrate why that is later. But we'll start here. So A, B, or C. So in this first rule, what I'm saying is here, the nMOS inputs ANDed together are in series, inputs ORs are in parallel. So what's going to happen is you're going to have two nMOS transistors. One of them's going to be hooked to A, one of them's going to be hooked to B. They're in series and they're both tied to ground. And then C is going to be in parallel, so it's 4, right? And so you can, and then you hook those two circuit paths to the output VI. And that's your pull-down network.
And at the bottom here is that there did exist an instance where there is not a combination that will create an output, invert the function, perform the steps, and then add an inverter on the output. We'll have an example problem where that is the case. So you can see precisely where that is. So then you perform De Morgan's law. So we have not and C, right? But then we're going to have not again. So then this would be not A or not B, right? So now that's our equivalent circuit. And then we use this rule 3. For the pull-up networks, pMOS inputs are ANDed together are in parallel, so it's the exact opposite, and the ORs are in series. So it's going to be the exact opposite. Of how, that shows how that works. So we'll do an example question, so hopefully that'll, and I actually have the exact algorithm with the problem.
When we, in the example question, for those of you who haven't taken the class before, I'm not going to expect you to write this on every problem. I want you to write it once so you get familiar with the algorithm, and then when you see it, you can just leave it out and just write the actual solution. I'll tell you what's appropriate to write. All right.
Okay. I know 115 probably sounds like a lot of gibberish, but once we go through a couple of example problems, it should make a lot of sense. Okay, so I'm going to scroll up a little bit here. So we're going with this first problem, example 1.1. We're going to do a two-input NAND using a CMOS pull-up, pull-down network by drawing the transistor layout. So
here I've just drawn a simple truth table where, let's say this was AND, right? So this is, these outputs would be 0, 0, 0, 1 instead of 1, 1, 1, 0. So here's what, if there doesn't exist an instance where there's not a combination that will create an output, meaning any instance where you have, right, so you have 0, 0, 0, 1, 1, and 0 for the first three, right? So it's all zeros on the outputs. In order for this to work, there would have to be a pull-down instance where a combination where you have a 0 would be able to place a 1 on the output. Since that doesn't work with AND, we can prove it here, right? Since that doesn't work with AND, we have all zeros. The only combination would be 1, 1. They get a 1 on the output, right? That means there's no combination there. We can get the appropriate current to flow through to get a 0, to get a 1 on the output. Likewise, when you have 1, 1, if you recall, pMOS are actually 4 conductors of 1s, right? So if you have a pMOS in the pull-up network, the VDD won't be able to get to the output either. So none of the outputs would work for a conventional AND gate. So what you have to do is to invert it like we've done here to a NAND gate where everything works fine, and then just put an inverter on the output. So what we're going to find out is the NAND gate will require 4 transistors, and a AND gate will require 6 because you require the extra 2 for the inverter. So let me scroll down here.
Just so you know, that's the solution. That's the only thing I'm really going to expect you to put on the TGO. Everything else is to explain the step-by-step. So for the pull-up network, the nMOS inputs ANDed together are in series. So this is
AB, right? So
the nMOS transistors are down here. So as you can see, they are in fact in series. And then you perform De Morgan's law. So NAND A and B becomes NAND A or NAND B. ORs are in parallel. So you can see these are in parallel, right? And now here's how this, let's see, did I include a diagram? No, I didn't. So I'll describe how this is actually physically working, kind of the same way with the inverter.
0, 0. 0 goes to all 4 transistors, right? Zeros, pMOSs are strong zeros. This is why I had the TGO, so you can actually remember this. 0, 1 will go out, and then again 0, 0, so 1 will go out. If you have a 0, 1, what's going to happen is this pMOS transistor is going to be off, right? And one of the pMOS transistors is going to be on. So if it's 0, 1, 0, this one will be off and B will be on. But since they're not both on, you can't have it flow through. But since one of these pMOS transistors is on, the 1 can still flow to the output. When it's 1, 0, it's the same thing except they're in reverse. 1, 0, this one's off, this one's on. Yeah, sorry. This one's on, this one's off. So we'll make sure they're backwards. Here, this one's on, this one's off. But there's still no complete flow through. And then when you get 1, 1, both pMOS transistors are finally off. So there's no way the 1 can flow out. We have 0, 0. Yeah, we have 1, 1. Then finally, both nMOS transistors are strong. The channels are created. You have a channel that goes through the source to the drain of this transistor, then to the source and to the drain of this transistor to the output. So that's how it logically works. And the reason why I introduced the De Morgan's law is when you start getting slightly larger equations, you can actually perform this to tell which ones are going to be in series and which ones are in parallel. So before, this is the pull-down network. If they're in series. You OR them, they're in parallel. And so then you can lay it out. Okay, so here, this is the only thing I'm expecting for example 1.2. But same thing, we've demonstrated, I kind of told you how this problem worked already, where this problem is do the 2-input AND gate using the transistor layout. So using that last portion of the algorithm, we can prove with 1, 1 here, if it's a NAND gate, we don't have an instance where you putting any 1s on the input. Since pMOSs are strong zeros, you have to have some instance of a 0 creating a 1 in order for the circuit to work. Likewise, since nMOSs are strong 1s, you have to have some instance where you can put a 1 on the input and get a 0 on the output. And that does happen here, but because of the pMOS it's eliminated. Okay? So what you do instead is you invert it and then do the exact same problem. That's 1.1. So this should just be simple. For 1.2, you just do the exact same thing and then add an inverter on the output. So I can explain this really quick. Here, this is VDD, this VDD, that's ground, that's ground. Does everybody understand what all of these symbols mean? I just want to make sure, just before. Yes, Colin?
Using the transistor with circle on the pMOS.
pMOS. So this is the pull-up pMOS with the circle on it. That's the pMOS transistor. Without a circle is an nMOS transistor. I believe 1.10, the one that I had is strong lead backwards. Those are drawn out properly on that one.
And we will conclude the problems with designing a 2-input NOR gate. So here, kind of doing the same thing, we can do NOR A or B. So they started out their OR, so it's parallel, right? So the nMOSs are going to be in parallel, as we see here. They're in parallel. And then what's going to happen is we can form De Morgan's law, right? De Morgan's law means this becomes AND B, right? So it says AND, that means they're in series. So that means the pMOS transistors are now in series. So by using that De Morgan's law trick, and we're going to be doing example questions later, probably during the next lecture, where you can have A and B or C or up to 5 variables, where by using that De Morgan's law, it actually makes the problem significantly easier. And I won't expect you to do this problem. We'll start with 1.4. So the homework assignment will be topical guide objectives 1.1 through 1.15 and examples 1.1 through 1.3. I'll take the next couple of minutes, kind of just briefly show 1.4. We're going to review this again at the beginning. 1.4 is not due. So here we have D or A and B or C, and it's all not, right? So we start out, we can use these parallel rules. So since D is in parallel by itself, it has its own lane, right? And then and is in series, so A is going to be in series. And since B and C are ordered, they're in parallel. So they're all coming from ground, they'll be hooked together, and then they have to go through this. So you can tie these equations and De Morgan's laws into actual CMOS paths. So then this step shows all of the, converting the De Morgan's law all the way through. So take the first step, it becomes not D and the remainder. And then here you break it down, this becomes A or B or C. And then the next step is changing this to not B and not C. And then what's going to happen is you can use that to determine the pull-up network. Here's D, and then A is going to be in parallel with B or C, and they all tie to VDD, and that's the entire thing. So we're going to start next class going over 1.4. Before I dismiss you, does anybody have any questions? We got 4 minutes. Feel free to ask anything about what we've covered. I'll include a note to ensure that one reminder of 1.10 that the graded and are report backwards in the notes. Does anybody have any other questions? Nobody feeling overwhelmed yet? Okay. So in that case, you are dismissed. I will post the video to YouTube, and I'll send out the link. And if you have nothing else, have a good day.